Okay. So on Wednesday, we stopped roughly here into explaining how does a computer or a processor executes a certain piece of program. And we said this program for any hardware is nothing other than a sequence of zeros and ones. But the way you understand them is through the contract of the ISA, right? And we said you load your program through some sort of an input device to the memory, right? So the first step is you get loaded from an input device to the memory. Once the program resides in the memory, the processor itself, which is in the my right hand side here, you read the instructions from the memory one by one through the control. So for example, you are executing this instruction for now, which is our add instruction. Then you bring it from the memory, so you fetch it, what we call a fetch stage, as you'll see later on. And once you fetch it from the memory, you decode it to understand it. So you have a sequence of zeros and ones. How do I know whether it's an add, subtract? What are the addresses of the registers? This is done through what we call a decode stage. So fetch, you obtain something from the memory to your registers through the control path of the processor. And decode means there is a decode unit. It's basically a bunch of decoders and gates that try to understand for this sequence of bits, what do we really mean? Are we adding R1, R2, R3? Are we multiplying to other registers to the results in R10? So all of this is being decoded through a circuitry that we usually call instruction decoder, right? And in a pipeline, it's called the decode stage. Once you're able to decode your instruction, so understand this message within this stream of bits, then based on this, you send control signals. That's why it's called the control path. You send control signals to the circuitry that really executes the actual operation, right? Like the ALU, for example, right? So the control path controls the data path to simply add the content of certain, like this is the add instruction, basically the decoder, and then you enable the data path to understand this is an add, and then you bring in the two registers, add them, and put them in the destination. Then after you execute, you need to store it back to the register, and simply I'm done with one instruction. So what is going to happen next? Do you think? So I went through the whole instruction execution. Then the processor will do what? Fetch the next instruction, exactly. So I'm done with this add. I'm going to bring the one afterwards and do exactly the same thing, right? But what else? Again, the same. One question though is how does really this control or the processor in general knows where to find the next instruction? Does anyone know? So we say this is a sequence of instructions in the memory. Yeah. Program counter. Thank you so much. And this is something that most probably you have dealt with in the embedded courses, right? Or how do you know about that? General knowledge. Dr. Nicholas, of course, 3GQ. Okay, so that's good. So usually, this is also very important for embedded interfacing stuff because you get closer to the instructions. But the idea is that there is a very special register called program counter that keeps the address of the next instruction to be executed. But the same question still holds. How does the program counter knows the address of the next instruction? So program counter is a place for that address. How do I know that address? What do you think? Yeah, but the pointer is the program counter, right? Which is the address. So the pointer from 2SH and 2SI, you know, a pointer is nothing other than an address, right? So it's the instruction address. But how do I know, for example, once I executed the add, where to go to find the next one? Yeah, increment the, oh, good. So it's a good idea. So we are in the right path. So we're incrementing the program counter, but the question is by how much should increment it? Yeah, by 1 word. By 1 word, yeah, this is 4 bytes, right? Who tells me that the instruction is 1 word? Because now you made an assumption that your instruction is 1 word, right? So this discussion is going exactly where I wanted to go. Basically, this whole thing is making an assumption that your instruction has a fixed width, right? because if it's not one word, I cannot really increase the program counter by one word, right? It might be 2 words. So one word assuming it's 4 bytes, 32 bits, right? So here, the assumption is that the instruction is 32 bits. So once you're done executing one, you jump to the subsequent one, right? With a fixed width, right? So why is very problematic for variable width instructions to execute. This is one problem with CISC hardware, that some instructions are variable width, and then the program counter need to do complex math to jump to the next one. But if all the time you have a fixed width instruction, 32 bits all the time, for example, then I know once I finish executing this one, I add 4, which is basically bytes, which is one word, to jump to the next one, right? So that's a good thing. But now, who tells me that the instruction is 32 bits for one word or 4 bytes? How do I know that? How does the hardware know that? Yeah.
Yes, just definitely can't go with the architecture.
Yeah. So one important aspect of that course is to demystify the terminology, right? When we say the architecture, we usually refer to the layer, the starting layer of the hardware beneath the ISA, right? So, which is this thing, that's the architecture. But the question is, how does the architecture know? When the architect architects the system to really increase the program counter by 4, why he thinks 4 is the right thing to do? Yeah,
It's specified in the ISA.
exactly. So our contract is ISA, right? So remember that these things are coming from software, right? Like I wrote my C code, the compilers, they generate them, and then I have the binary file, then I load to the memory. So these things are already generated completely in the software layer, regardless of what is your target hardware, right? Only there is one contract that you maintain when you do this. It's regardless of your hardware details, except the fact that you assume I'm targeting a certain instruction set. So if this is, for example, a RISC maps instruction set, then you know that my instruction is a 32-bit. And the back end of the compiler, when generates this binary file, the assembler, right? It will create 32 bits that represent this instruction, right? As we said on Wednesday, even though it's not only the width, but also the values here, right, are dictated by the instructions. Because if you open an instruction set, and we would have a few examples here. If you open an instruction set manual, you will find that for every single instruction, you define what we call a register field that tells you the width, the different fields of every instruction, like the opcode, the destination, the register, and then also the width of every one, right? Without that contract, there is nothing you can do, either in hardware or in software, right? Because everyone will be in disagreement and nothing can interplay together nicely. Make sense? Good. So another question here. If I do what I'm doing right now, by all the time increasing the program counter by 4, I am overlooking my program, right? Because the sequence of the program is not all the time you execute one instruction after the other, right? So there are other cases. What would be these cases? Yeah, a jump or branch. Yeah, like what are examples of like a jump or branch instruction from the C high level? If statement is one thing. Yeah, thank you. Calling a function is another thing. Thanks. What else? Recursion, yeah, it's also another thing. Thank you. Yeah. Yeah. Go to, yeah, but go to is a little bit uncommon, but that's a very direct way of jumping. Yeah. Loops, exactly. Thank you. So loops, in fact, are the most common. Loops and conditional statements are the most common pieces of code in any real program. Like, and we will see this when we do the labs. If you take any real benchmark or any real application, you will find that it's composed of large portion of the code embedded in loops. This is how you optimize your code, right? So loops, conditional statements, functional calls, goto, all are examples of branches and jumps. The problem with this kind of control instructions, we call them control instructions because they control the path of the program, is program counter for the next instruction is not necessarily program counter plus 4, because I'm not, for example, if this is a jump instead of being an add, well, let's not talk about assembly. This is an if statement, right? That will translate into a branch. If the condition is true, I might go to the next instruction. If the condition is false, I might just go to a completely different place. So the program counter need to know whether you bring the next instruction or the one after, I don't know, X offset, right? So branches mess with the program counter easy calculation, which is adding program counter +4, right? This is one thing that will benefit a lot from when we come into like how we do pipelining and how does this the control these hazards and how we resolve them. A big deal of computer architecture is also trying to resolve this corner. It's not a corner case, it's very common, but to resolve these particular branching scenarios. Good? Sense? Okay. So generally I fetch the next instruction if I dealing with branches. Then the simplest format of operation is fetch an instruction from the memory, decode it to understand, send the selection lines to the data path. The data path will execute, and then the control will bring the next instruction from the memory and keep doing this all the time. Good. So a third observation, if I'm doing this in that way, which is fetch one instruction, decode it, execute it, and then bring the next one, this is completely inefficient, right? Why that's the case? Okay, so we keep saying control path and data path. What is this really? So a control path is, well, as you said, it's mainly composed of decoders and gates, multiplexers that decide which, first of all, multiple things. What is the next instruction that I'm going to execute? And the input from the memory, that's simply the data that I need to bring in the fetch stage, right? And then I also need to decode that instruction to understand it, as we said. Once I decode it, I need to send signals, what we call selection lines, to the basically control the data path. Think about the ALU, for example, where you have an adder, multiplier, subtractor, shift registers, all these things. And then you enable, disable them based on the type of the instruction. If I have an add, enable the adder. If I have a subtract, enable the subtractor. If I have a multiply, enable that or that, right? There are selection lines that are created by the decoder or the control path. Good. So this is what the control path is doing. With the data path, this is the one that is performing the actual operation, right? So it's the ALU itself, if you're talking about arithmetic operations, or it's the logic needed to bring something from the memory if it's a load or store instruction. So you execute the instruction, and we call them usually function units, right? Again, adder, multiplier are examples, or also there are what we call storage locations or memories. We deal with register files, we deal with caches, we deal with buffers, and we'll come into this in a separate page. In addition to the data, well, something in addition to the function unit and the storage in the data path, we need buses, right? Because go back to our example of the add instruction here. Let's say we have an animation here. Yeah, this one. So we said, okay, I realize this is an add instruction. Then I need to bring in my operands, right? This one and this one to do the addition on. So I'm adding R4 and R2, which are two registers, and storing the results in R2. Those are registers stored in the register file, right? So it's a storage. I have their address, go back and bring them. But what does it mean to bring them, right? These are bits. So they need wires to be transferred on, right? So there are buses, wires, throughout the data path to bring something from the register file, to write something to the register file, to write something to the cache if it's a memory operation, right? So you need interconnect basically between the function units and the storage you have. And how to optimize this interconnect is also a big deal in computer architecture because it becomes a bottleneck, right? Especially if you have massive data to deal with. And then data path deals with the register file, but also deals with storage memory. As we said, caches. So you load data from the memory or you store data to the memory if you have a load or store operation. Okay, then the last stage is once I'm done executing all my instructions and I wrote the results back to the register file and then maybe to the memory, your program might be outputting something to an output device. Like again, think about 2SH, you did CNC out or fprintf or fopen or fread, fwrite, dealing with files or dealing with the console. Then if you want to output something, you need to deal with an output device, right? Okay, so as we have seen in this discussion, many of the things really dependent on the fact that there is an instruction set architecture that works as a contract between the two worlds, right? And if this contract is breached for somehow or incorrect, this something either in software incorrect or hardware incorrect, nothing is going to work. Right? So here is just an example of such an instruction set, which I'm using the MEPS one, but I'm using the MEPS one in these slides because it's very simple to understand. But again, that the discussion applies. MEPS is a RISC instruction set. If you want to step back. So instruction sets, there are multiple of them, but usually they are categorized into two main categories. One of them is called RISC, the other one is called CISC. A RISC instruction set is reduced instruction set. It's a one that appeared in early 80s. So the CISC one was in fact before the RISC. And well, there is a nice history for this. I can share with you articles, talks about that history. But in early days of computers, compilers were behind in development, right? Software was basically the one that is behind. Hardware was the one at the front, right? This was like in 70s and 60s. So hardware companies like Intel and IBM, the major players back then, and Motorola as well, and a few others that faded out. So, well, I have powerful hardware, but I don't have enough software. So if you remember, or if you watch any of these documentaries, you used to program your hardware using bunch cards, right? So there's no software at all either, right? So the software was way behind the hardware. If this is your scenario, what you do, you basically rely on the hardware to make it more complex because you have a very simple software. There are no compilers. People usually program directly in assembly, right? Or even there were low-level languages like C and Fortran. It was also low-level, and compilers weren't optimized for that. So they came up with this idea of CISC instruction set. For the reason that the hardware was more advanced, then you can do more things on hardware. So for example, you allow variable length instructions. You allow any instruction to do any operation, like for example, in Intel, move instruction, moves data between registers, moves data between memories and registers, and even moves data between memory and memory. Which is something crazy nowadays, right? No one is really doing this in modern days. The reason is instructions were very powerful. So in fact, it's not a single instruction. It's a function on its own, to the level that, for example, x86 would have a function called swap. Right now, we write a function in C that's called swap, right? So instructions are complex, so they execute multiple operations, right? That's the main idea of CISC, is that in CISC instructions are complex and they execute multiple operations. Why? Because the hardware was complex enough to allow this, and it was very hard to write software. So you simplify your software by combining multiple operations in one assembly instruction, and then you allow the hardware to execute it, right? Over the time, software catched up, and then it also became more advanced than the hardware, right? So compiler advancement became way better, and then writing assembly. Right now you have early enough the applications were easy and they were mainly scientific, but later on applications became way more complex, commercial users that are not really expert users. So it reached to the level that software, you no longer can really do these complex encodings in software, and software can be way simplified and also better optimized because compilers were in a very good state, right? And then hence in 80s came the RISC instruction set. What is the RISC instruction set? It said, okay, this whole mess of allowing one instruction to do whatever it wants and so many operations is complicating the hardware a lot and making it non-modular. So instead, we're going to make every single, the philosophy of RISC instruction sets in general, whether it's MEPS, ARM, PowerPC, or something else, then the main idea is every single instruction does a single thing, right? If you need to execute multiple operations, you have to write multiple instructions. So if you want to move data between two memory operations, two memory locations, this cannot happen in a single instruction. You have first to bring it from the memory to a register, and then write it from a register to another memory location. If you want to add two memory operations, you first bring the data from the memory through a load, you do the addition through an add instruction, and then you do a store in the memory with a store instruction. In Intel machine, add allowed operations on memory operations. So in a single add, you are able to add two memory locations, store the results back in another memory location, right? So a single instruction right now is being translated into 3 or 4 instructions. Why this is a good idea? Well, because this simplification allows you to optimize your hardware significantly. It allows for better compiler optimized code because now the instructions are simpler. So I don't need to do a lot of backing, right, into one instruction. And then because the hardware is simpler, I can put more of that hardware in the circuit. And also I consume, and that's the key point, I consume much less power, right? And that's the main reason why Intel failed completely in the mobile market, right? Because it wasn't because it's very high cost or not because of technology, it's because of power consumption, right? So your performance that you are gaining from the CISC is consuming so much power to the level that, well, it will not really work for most of the modern applications, embedded devices, mobile phones, wearables, automotive, avionics, whatever embedded world it is, right? So this is also another reason why Intel is still the dominant market player in the server domain. Why? Because in server, well, you don't care much. Well, they will right now care about power as well, but not as much as your like smartwatch, right? So in a server, you have a plug-in direct connection to electricity. It's cheap around the world. They put it in places where it's very cheap to get electricity. So they care less about power consumption, right? And because you still can get significant performance, then, well, Intel is still leading there, right? Things changing over time, but that's the general perception, right? And this is the history of, well, RISC versus CISC, right? Good. Is there any question? Does it make sense? So among the category of CISC, the most common one is x86, right? The Intel is really the dominant one, and well, AMD as well, AMD 64 and the alternatives of that, they are also still CISC instruction set. And by the way, Intel at one point they wanted to move to RISC, they didn't manage to do it. So in reality, right now, in all the machines that are Intel powered, they have one layer beneath the instruction that they translate the instruction into what they call intermediate opcodes, intermediate instructions. So to simplify the hardware while not breaking compatibility, what they do right now is, well, you write your software as it is, the compiler will create the complex instructions, but we do one layer to really simplify the instructions, break them down into the multiple ones as if we are RISC. Why? Because we want to simplify our hardware, right? That's one way that Intel is trying to get into those markets by simplifying the hardware while not breaking backward compatibility into their complex CISC instruction set. Okay. With the RISC category, there are many common ones. ARM is a dominant one, especially in mobile and embedded devices. There is the MIPS instruction set, which is well, there were MIPS machines, but right now they are less common. And the new market player is RISC-V, right? That's the one that is gaining a lot of traction everywhere because it's an open source instruction set. Anyone can take the instruction set. The problem with the ARM instruction set, it's proprietary. You cannot really go ahead and implement a processor that uses the ARM instruction set, right? And ARM will sue you, right? So you have to license it from them, right? And it's millions of dollars of cost, right? So it's a monopoly. And well, once there's a monopoly, people will try to find a way out. And then, similar to Linux open source and software, this RISC-V instruction set, open hardware, is the movement that is going on right now in the domain of computer architecture or the domain of computing machines to be able to develop and transfer and advance and verify a state-of-the-art hardware that is open source, right? Good. Questions? Okay, so for the MIPS ISA, we use it as an example of just trying to decode how you can read an instruction set manual. Because once you are able to do it for a MIPS, you do it for anyone, right? So usually, as I was telling you, if you open the PDF, you find it on the internet, you simply have a bunch of these register descriptions, right? It tells you for every instruction format or type, they divide the instructions into multiple formats. For every instruction format, it tells you what is basically the fields, how to interpret which bit is which, right? That's the main question that the ISA is trying to answer. If I look into a bunch of bits of an instruction, how do I know that bit 13 is one of the address bits of my source register, or bit 15 is the opcode, right? This is basically the main question. And there are three main instruction formats in MIPS. One of them is mainly related to jump for obvious reasons, that jump is a very special type of or branching in general. is a very special type of instruction. We call it control instruction, where in that case you have the opcode and then you have the jump target action. Good. And then there are also the arithmetic ones, like similar to the add, for example, where you have an opcode. This is the add instruction, for example, and then you have two sources and one destination. Well, I don't recall, I guess in maps, the destination comes the third one. These are the two sources, source one, source two, and that's the destination. I will try to remember what is SA, but I guess I have one slide for this. But the important part is that because opcode is limited, and opcode usually is used to distinguish between categories of instructions, you need some additional bits to differentiate between instructions of the same format. What do I mean? Add and subtract are both arithmetic instructions, right? So they might end up having the opcode the same. So it's not enough to say that, well, this opcode is an indication of an add. If you go back to the example we had here, thank you. If you go back to that example, to determine that this is an add, we needed to look into this opcode, right? If you look into the format we have been looking at, we had an opcode, and then we had an opcode, and then we had sources and destinations, these three ones, and then this is the functionality part, right? So to know that this is an add, you need to look into these two fields together, right? But for the hardware to know this, it first looks into the opcode, because that's the constant part across all instructions. Once it determines it's, for example, all zeros, so it's part of arithmetic, then I go to the functionality and try to understand what's really happening, right? That's basically the mindset here. Okay, so I guess we are good in terms of ISA. So the part, so we don't want to delve into details of ISA. Maybe later on we will have also another lecture. We need to use it, but you have to make sure you understand that the intuition is that the purpose is not to understand how the MIPS is being written. You don't have to memorize anything of that, or basically because you can open the instruction set manual and you know all of this. The important part is how to read it, right? How to open a manual and make sense of it, right? So what we said right now is a summary. If I open a manual, I need to look into what are the main formats, right? Usually there are immediate formats, like we talked about the arithmetic ones. There are ones that deal with immediate values. If I want, for example, to add 4 plus, like 4 as an immediate value to a registered value with the result in another value, then you need to compare immediate value, right? So these are the immediate instructions. And then there are arithmetic ones and the jump ones. Sometimes we put the load and stores, well, it depends on the formats. Most instruction sets, they will have a separate one for load and store, what they call memory instruction format. In MIPS, I guess it depends, it can be here or here based on whether you are using really indirect addressing or not, whether you're using an immediate value to determine your address or you are using immediate value plus a register. It's a bit of a detail. But the main idea is that the main formats you can think of control instructions, branch, jump, whatever it is, arithmetic operations or register-based instructions and immediate-based instructions, right? This and we said memory can be a separate one or between immediate and register-based in different instruction sets.